Did you know that the atoms in your body were forged in the hearts of stars? Billions of years ago, these stars exploded. They scattered their enriched guts across the galaxy. This stardust eventually formed planets and life, including you. Physics is the story of how this all happened. It's the quest to understand the fundamental rules governing the universe, from the tiniest quark to the largest supercluster of galaxies. It's a grand adventure of discovery, full of wonder. Imagine the universe as a vast, intricate clockwork. Physics seeks to understand its gears and springs. Physics asks the big questions. Why is the sky blue? What keeps us stuck to the earth? What is light? How did the universe begin? These are not just philosophical musings. They are questions that physics attempts to answer with evidence and mathematics. The answers often reveal a universe far stranger and more wonderful than we could have ever imagined. It's a journey that stretches our minds and expands our cosmic perspective. It connects us directly to the cosmos. We are, after all, a way for the cosmos to know itself. The beauty of physics lies in its universality. The same laws that govern the fall of an apple also dictate the orbits of planets. The principles that explain the light from your lamp also describe the light from distant stars. This consistency is profound. It means that by understanding physics here on Earth, we can unlock secrets of the farthest reaches of space and time. There's an underlying order to the apparent chaos of the universe. Physics is our tool for perceiving this order. It's a language spoken by the cosmos itself. Join us on this journey through the world of physics. We will explore its core ideas in simple terms. We will meet the brilliant minds who unveiled these truths. We will see how physics shapes our everyday lives and our future. You don't need to be a rocket scientist to appreciate the elegance of the universe. You just need curiosity. So let's open our minds and prepare to be amazed. The universe is waiting to share its secrets. Let the cosmic symphony play. So what exactly is this thing we call physics? At its heart, physics is the most fundamental of the natural sciences. Its ultimate goal is to understand how the universe behaves. It explores matter, its motion, and its behavior through space and time. It also studies the related entities of energy and force. Think of it as the instruction manual for reality. It seeks to find the most basic rules that everything in existence follows. These rules are often expressed in the language of mathematics. They are precise and powerful. Let's talk about matter. Matter is the stuff that makes up everything you can touch and see. Your body, your chair, the air you breathe, the distant stars, it's all matter. Matter is made of tiny particles called atoms. Atoms themselves are made of even smaller particles, protons, neutrons, and electrons. And even these are made of still smaller things called quarks. Physics explores the properties of matter. It studies how these fundamental building blocks interact to form the world around us. It looks at solids, liquids, gases, and even more exotic states like plasma. Then there is energy. Energy is the capacity to do work. It comes in many forms. Kinetic energy is the energy of motion. Potential energy is stored energy, like a ball held high. Thermal energy is heat. Chemical energy is stored in bonds between atoms. Nuclear energy is locked within the atom's core. A key idea in physics is the conservation of energy. Energy cannot be created or destroyed. It can only change from one form to another. This principle governs everything from a light bulb to a supernova. Physics is the study of how matter and energy interact. These interactions are governed by fundamental forces. There are 4 known fundamental forces: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. These forces dictate how objects move, how light travels, how atoms hold together, and how stars shine. Albert Einstein famously showed a deep connection between matter and energy with his equation E = mc2. This revealed that matter can be converted into energy, and energy into matter. Physics constantly seeks these deep, unifying principles. Our journey into the specifics of physics often begins with classical mechanics. This is the physics of the everyday world. It describes the motion of objects we can see and touch. Think of a thrown ball, a spinning top, or planets orbiting the sun. Classical mechanics provides a remarkably accurate description of these phenomena. It was the first great triumph of physics. It showed that the universe operates according to understandable laws. It laid the groundwork for much of the science and technology that followed. The towering figure in classical mechanics is Sir Isaac Newton. Born in England in the 17th century, Newton was a true genius. He made revolutionary contributions to mathematics, optics, and of course, physics. Legend has it that an apple falling from a tree inspired his thoughts on gravity. While the apple story might be a simplification, his insights were profound. He formulated the laws of motion and the law of universal gravitation. These ideas fundamentally changed our understanding of the physical world. He gave us a framework to predict and explain motion. Newton's first law of motion is the law of inertia. It states that an object at rest will stay at rest. An object in motion will stay in motion with the same speed and in the same direction unless acted upon by an unbalanced force. Think about a hockey puck gliding on ice. It keeps moving until friction or a hockey stick stops it. Newton's second law relates force, mass, and acceleration. It's famously expressed as F equals sine ma. This means that the more force you apply to an object, the more it accelerates. Heavier objects require more force to accelerate at the same rate. Newton's third law of motion states that for every action, there is an equal and opposite reaction. When you push against a wall, the wall pushes back on you with equal force. This is why rockets work. The rocket expels hot gas downwards, action. The gas pushes the rocket upwards, reaction. These three laws, together with his law of gravitation, provided a complete system for understanding motion on Earth and in the heavens. Newton's work was a monumental achievement, a testament to the power of human reason. Beyond his laws of motion, Isaac Newton gave us the law of universal gravitation. This law is truly cosmic in its scope. It states that every particle of matter in the universe attracts every other particle. The strength of this attraction depends on the masses of the objects and the distance between them. This is the force that keeps your feet firmly planted on the ground. It's the force that holds the moon in orbit around the Earth. It's the force that keeps the Earth revolving around the sun. It sculpts galaxies. We see gravity's effects everywhere. It causes the tides in our oceans, pulled by the moon and the sun. It dictates the path of a baseball thrown into the air. It governs the majestic dance of planets, moons, and comets within our solar system. Before Newton, the motions of celestial bodies were mysterious. After Newton, they became predictable. His law allowed astronomers to calculate planetary orbits with astonishing accuracy. It was a powerful demonstration that the same laws apply in the heavens as on Earth. This unified view was revolutionary. However, Newton's theory of gravity had a puzzle at its core. It described gravity worked with incredible precision, but it didn't explain it worked or the force was transmitted across empty space. Newton himself was troubled by this action at a distance. How could the sun exert a pull on the Earth across millions of miles of emptiness instantaneously? He famously said, "I frame no hypotheses, hypotheses non fingo," on this matter. He knew his theory was a description, not a complete explanation of gravity's fundamental nature. Despite this conceptual mystery, Newtonian gravity remains incredibly useful. For most everyday purposes and many engineering applications, its predictions are highly accurate. We use it to launch satellites, navigate spacecraft, and build bridges. It was the dominant theory of gravity for over 2 centuries. It was only with the arrival of Albert Einstein in the 20th century that a new, deeper understanding of gravity would emerge. But Newton's contribution was the essential first step, a giant leap for humankind's understanding of the cosmos. Section 5. The Quantum Leap, a strange new world of particles. As the 19th century turned into the 20th, scientists believed they had a good grasp of physics. Newton's laws and Maxwell's theory of electromagnetism seemed to explain almost everything. But then experiments began to reveal phenomena that classical physics couldn't explain. These puzzles arose when scientists started probing the very small, the world of atoms and their constituents. It became clear that the rules governing the macroscopic world didn't quite apply at these tiny scales. A new kind of physics was needed. This was the dawn of quantum mechanics. The first clues came from studying light and heat. Max Planck in 1900 proposed a radical idea to explain the radiation emitted by hot objects. He suggested that energy didn't come in continuous amounts like water flowing from a tap. Instead, he said energy comes in discrete packets or quanta. It was like saying energy could only be bought in specific coin denominations, not any arbitrary amount. This idea of quantization was revolutionary. It marked the birth of quantum theory. Soon after, the structure of the atom itself began to be unraveled, revealing electrons, protons, and neutrons. Niels Bohr, a Danish physicist, applied Planck's quantum idea to the atom in 1913. He proposed a model where electrons orbit the nucleus only at specific energy levels. They could jump between these levels by absorbing or emitting a quantum of energy, a photon of light. This model successfully explained the characteristic patterns of light emitted by different elements, known as atomic spectra. However, the quantum world was proving to be very strange indeed. Particles didn't always behave like well-defined little balls. Their properties seemed fuzzy and uncertain until measured. Quantum mechanics introduced concepts that challenge our everyday intuition. One such idea is the Heisenberg uncertainty principle. It states that you cannot simultaneously know certain pairs of properties of a particle with perfect accuracy. For example, the more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. This isn't due to faulty measuring instruments. It's a fundamental feature of nature at the quantum scale. This strange new physics underpins much of modern technology, from lasers and transistors in your computer to medical imaging techniques like MRI. Section 6. Waves or particles. The enigma of duality. One of the most mind-bending concepts in quantum mechanics is wave-particle duality. For centuries, light was thought to behave like a wave. Experiments like Thomas Young's double-slit experiment in the early 1800s showed this clearly. When light passes through two narrow slits, it creates an interference pattern on a screen behind them. This pattern of bright and dark bands is characteristic of waves interfering with each other, like ripples on a pond. This seemed to settle the matter. Light is a wave. Case closed, or so it seemed. But then, in the early 20th century, Albert Einstein came along. He explained a phenomenon called the photoelectric effect. This is where light shining on a metal surface can knock electrons off it. Einstein proposed that light also behaves as if it's made of tiny particles, or quanta, which he called photons. The energy of each photon depends on the frequency of the light. This particle nature of light was necessary to explain the details of the photoelectric effect. So, which is it? Is light a wave or a stream of particles? The answer, strangely, is both. The story got even weirder. In 1924, a young French physicist named Louis de Broglie made a bold suggestion. If light waves can act like particles, he reasoned, maybe particles like electrons can act like waves. It was a radical idea, but experiments soon confirmed it. Electrons, when fired through a crystal lattice or a double slit, also produced interference patterns, just like waves. This wave-particle duality isn't just for light and electrons. It seems to be a fundamental property of all matter and energy at the quantum level. Everything has both wave-like and particle-like aspects. The implications of this duality are profound. Whether something behaves as a wave or a particle can depend on how you try to measure it. The very act of observation can influence the outcome in the quantum realm. This led to the development of a probabilistic view of quantum mechanics. We can't always predict the exact outcome of a quantum event. We can only calculate the probabilities of different outcomes. The universe at its most fundamental level seems to operate on chance and uncertainty, a far cry from the deterministic clockwork universe of Newton. Section 7. Einstein's Revolution, Reshaping Space and Time with Relativity. As quantum mechanics was rewriting the rules for the very small, another revolution was brewing. This one concerned the very large space, time, and gravity. And its chief architect was Albert Einstein. Even before his work on the photoelectric effect, Einstein had been grappling with inconsistencies between Newton's mechanics and Maxwell's theory of electromagnetism, particularly concerning the speed of light. His insights would forever change our understanding of the fabric of the cosmos. He gave us not one, but two theories of relativity. In 1905, his Annus Mirabilis, or Miracle Year, Einstein published his theory of special relativity. It was built on two simple-sounding postulates. First, the laws of physics are the same for all observers moving at constant speeds. Second, the speed of light in a vacuum is the same for all observers, regardless of the motion of the light source or the observer. This second postulate has bizarre consequences. It means that space and time are not absolute, as Newton had assumed. Instead, they are relative and intertwined into a four-dimensional fabric called space-time. Special relativity predicts strange effects. Time can slow down for moving observers, time dilation. Lengths can contract in the direction of motion, length contraction. And perhaps most famously, mass and energy are equivalent, as expressed by the iconic equation E equals mc squared. This equation shows that a small amount of mass can be converted into a tremendous amount of energy, the principle behind nuclear power and nuclear weapons. Special relativity applies to objects moving at constant speeds. But what about acceleration? And what about gravity? That required another leap. 10 years later, in 1915, Einstein unveiled his masterpiece, the theory of general relativity. This was a new theory of gravity. Einstein proposed that gravity is not a force pulling objects together, as Newton thought. Instead, gravity is the curvature of space-time caused by the presence of mass and energy. As the physicist John Wheeler famously put it, space-time tells matter how to move. Matter tells space-time how to curve. Massive objects warp the space-time around them, and other objects follow these curves. This is what we perceive as gravity. It's a geometric theory of gravitation. Section 8. A tapestry of discovery, milestones, and minds in physics history. While Newton and Einstein stand as colossal figures, the story of physics is a rich tapestry woven by many brilliant minds. Long before Newton, thinkers like Galileo Galilei laid crucial groundwork. Galileo's experiments with falling objects and his telescopic observations challenged ancient ideas. He championed the importance of observation and experimentation, the cornerstones of the scientific method. His work on inertia paved the way for Newton's laws of motion. He truly set the stage for modern physics by insisting that nature speaks through mathematics. The 19th century saw incredible progress in understanding electricity and magnetism. Michael Faraday, a largely self-taught genius, discovered electromagnetic induction. This is the principle behind electric generators and transformers. James Clerk Maxwell then took Faraday's experimental findings. He unified them into a set of elegant mathematical equations. These equations described all electric and magnetic phenomena. Astonishingly, Maxwell's theory predicted the existence of electromagnetic waves traveling at the speed of light. This revealed that light itself is an electromagnetic wave, a profound unification. The study of radioactivity at the turn of the 20th century opened new windows into the atom. Marie Curie, a pioneering scientist in many ways, conducted groundbreaking research on radioactivity. She was the first woman to win a Nobel Prize, and the only person to win Nobel Prizes in two different scientific fields, physics and chemistry. Ernest Rutherford, through his famous gold foil experiment, discovered that atoms have a tiny, dense, positively charged nucleus at their center. This overturned the previous plum pudding model of the atom and set the stage for Bohr's quantum model. The quest continues with contemporary physicists. Richard Feynman contributed significantly to quantum electrodynamics, QED, our best theory of how light and matter interact. Murray Gell-Mann proposed the existence of quarks, the fundamental constituents of protons and neutrons. Stephen Hawking deepened our understanding of black holes and the origins of the universe. Physics is a collaborative, international endeavor. Discoveries build upon previous work, often spanning generations and continents. From ancient philosophers wondering about the cosmos to scientists at the Large Hadron Collider smashing particles, the journey of discovery is ongoing. Section 9. Conclusion. Physics, our compass to the future. We have journeyed from the predictable world of falling apples and orbiting planets, governed by Newton's classical mechanics. We delved into the bizarre, probabilistic realm of quantum particles, where reality itself seems to shimmer. We then soared through Einstein's universe, where space and time bend and warp to the tune of mass and energy. Physics, in its essence, is humanity's grand attempt to read the cosmic rulebook. It's a story of breathtaking scope, from the infinitely small to the infinitely large. It is a testament to human curiosity and ingenuity. The importance of physics extends far beyond academic curiosity. It is the bedrock of modern technology. The principles of electromagnetism power our cities and our devices. Quantum mechanics is the foundation of the digital revolution. Computers, smartphones, lasers, and modern medicine. Relativity is essential for technologies like GPS to function accurately. Understanding physics allows us to harness the forces of nature, to innovate, and to solve some of the world's most pressing challenges, from developing sustainable energy sources to exploring new frontiers in medicine and materials science. Yet, for all we have learned, the universe still holds profound mysteries. What is dark matter, the invisible stuff that seems to outweigh all visible matter in galaxies? What is dark energy, the mysterious force causing the expansion of the universe to accelerate? How can we reconcile general relativity and quantum mechanics into a single theory of everything? These are the grand challenges that drive physicists today. The frontiers of physics are vibrant with new questions, new experiments, and the promise of even deeper understanding. The adventure is far from over. Ultimately, physics is more than just equations and experiments. It is a way of thinking. It encourages critical thought, problem-solving, and a deep appreciation for the intricate beauty and order of the cosmos. It offers us a cosmic perspective, reminding us of our place in a vast and ancient universe. As we continue to explore its laws, we not only uncover the secrets of the universe, but also learn more about ourselves and our potential. Physics is our compass, guiding us as we navigate the complexities of an ever-evolving world and reach for the future.